So in this session on signals and systems, we are going to study continuous time Fourier transform. Now in our last session, we have studied that Fourier series is applied to periodic signals in order to find the frequency spectrum. However, for non-periodic signals, Fourier series is not useful. So we are going to study Fourier transform. So let us start. As I have said, Fourier transform is applied to non-periodic signals, and let us just revise a little bit of our classification of signals which we have done last time, but let's repeat it for convenience. Signals can be subdivided into two types. One is periodic and the other is non-periodic signal. And we have seen that for periodic signals, Fourier series can be used and you can obtain the frequency spectrum. Now, what is a non-periodic signal? Clearly, it is a signal which never repeats itself. Or you can play a mathematical trick and say that it repeats itself after infinite time, which is as good as saying that it never repeats itself. So it is called as a non-periodic signal. So its time period approaches infinity. Now, let us see some examples of non-periodic signals. Finite duration signals. These class of signals are basically non-periodic. For example, consider a single rectangular pulse. And before this pulse occurs, the signal has a zero value. And after the occurrence of the pulse, again it has a zero value. So it never repeats itself. And this will apply to any finite duration signal. Okay. Another type of non-periodic signal is a random signal. For example, noise is a random signal. Any information carrying signal is also random in nature. So since it's truly random in nature, it never repeats itself, or you can say that it repeats itself after infinite time. So these are a couple of examples of non-periodic signals. Okay. And what we are going to do is to develop the approach for finding the frequency spectrum for non-periodic signals. And the tool that we are going to use is the Fourier transform. Now, before we get into the mathematics of this Fourier transform, let us say a couple of points about the spectrum of a non-periodic signal. Now, there are two important distinctions from Fourier series. And what are these? One is that spectrum is continuous. And the second is that amplitude spectral density is useful rather than the amplitude itself. And this comes about because of the fact that spectrum is continuous. If the spectrum is continuous, it means that even in a finite range of frequencies, the number of possible frequencies are infinite. So the amplitude of each frequency component will become infinitesimally small. And there is no point in talking about the amplitude of the signal at a definite frequency. So the concept that is more useful is amplitude spectral density rather than the amplitude itself. But let us try to address this statement, spectrum is continuous. How does it come about? So to obtain this spectrum, we first start with a periodic signal and then allow the period t to become infinity. Alright. So first consider a periodic signal with t equal to 1 second. If t is equal to 1 second, that is the time period, then clearly the fundamental frequency is reciprocal of this. So that is 1 divided by t, which is 1 itself, and that is your f0 fundamental frequency, that is 1 Hertz. So clearly the second harmonic will be 2 times this, that will be 2 Hertz. Third harmonic will be 3 times this, that will be 3 Hertz. Now if you look at the difference between the successive frequency components, this is 2, this is 1. So 2 minus 1, that is 1. This is 3, this is 2. So again the difference is 1. So if you consider the difference between any two successive frequency components, it's always equal to 1 Hertz. Now this is the case with a periodic signal which has a time period equal to 1 second. But let us consider a periodic signal whose time period, let's say, is 10 seconds. Then what will happen? Now this I have already said. For this, the difference between successive frequency components is 1 Hertz. But let us now consider that the time period is 10 seconds. In that case, it's easy to see that the fundamental frequency will be 1 by 10, which is 0.1 hertz. Second harmonic will be zero point 0.2 hertz and so on. So in this case, you find that the difference between successive frequency components has reduced from 1 hertz, it has become 0.1 hertz. So as you go on increasing the value of t, this difference between successive frequency components goes on decreasing. And eventually in the limit, as t approaches infinity, you can imagine that the difference between the successive frequency components will become infinitesimally small, essentially zero, and therefore what was a discrete spectrum for periodic signals becomes a continuous spectrum for non-periodic signals. All right. So I have already said this, as t approaches infinity, the difference approaches zero and the spectrum becomes continuous. Okay. Now what we are going to do is to derive the expression for the Fourier transform of a non-periodic signal. So what we do first is, suppose I have xt like this. So this is a single non-recurring pulse, a single pulse, which is triangular in nature. Now I suppose I consider consider a signal which is periodic in which is periodic in time, but has a nature similar to this. So if you compare xt and x hat t, you find that xt contains only one pulse, whereas x hat t contains periodic pulses. So this is a periodic signal. Now this is minus t by 2 and this is plus t by 2. So if I go on increasing t, this will shift to the right and this will shift to the right. And as t approaches infinity, x hat t will become equal to xt. Therefore, we can say that xt, which is a non-periodic signal, can be obtained from a periodic signal by allowing t to approach infinity. So basically what we are going to do is to write the expression for the coefficients of the Fourier series for x hat t, which is a periodic signal, then apply the limit and therefore obtain the Fourier transform. That is going to be our approach. All right. So if you consider x hat t, which is periodic, and find the Fourier coefficients considering the exponential form of the Fourier series, then xn, as we already know, is 1 by t minus t by 2 to plus t by 2 x hat t e raised to minus j n omega naught t dt. This we have studied in our earlier sessions. Now as t approaches infinity, xn approaches 0. It's easy to see this. This is 1 by t. So as t approaches infinity, xn approaches 0. So there is no point in trying to calculate xn for a non-periodic signal. So what we do is, in order to resolve this difficulty, we multiply both sides of this equation by the time period. In that case, we get xn multiplied by t equal to this part of the right hand side, which is written here. And now we can apply the limits for t approaching infinity. So limit t approaching infinity, xn multiplied by t is limit t approaching infinity and this entire right hand side. Now, when we apply this limit, what are the changes in the right hand side? First of all, note that the limits of integration will become minus infinity to plus infinity. X hat t itself will become xt, as we saw in the last slide. Now, as t approaches infinity, omega naught approaches in infinitely small value, infinitesimally small value. So n multiplied by omega naught becomes essentially a continuous variable rather than a discrete variable. So let us see this. As t approaches infinity, limits become minus infinity to plus infinity. X hat t approaches xt and n omega naught, which is a discrete variable, becomes a continuous variable. So when we substitute all this, limit of t approaching infinity, xn multiplied by t is equal to minus infinity to plus infinity. Note that the limits have changed. X hat t has become xt and e raised to minus j n omega naught t has become e raised to minus j omega t dt. Now if you look at this right hand side integral, you will find that the integration is with respect to time, the time variable. So when you integrate this and put the limits, clearly the right hand side will be just a function of omega. Therefore, we can write this equation as x omega. The left hand side can be written simply as x omega, that is minus infinity to plus infinity xt e raised to minus j omega t dt, and this is called as the Fourier transform of xt. Alright. So we have obtained the Fourier transform. That means x omega in terms of xt. But can we obtain xt in terms of x omega? So let us do that exercise now. Inverse Fourier transform. So again we start with the expression for x hat t, which is a periodic signal, and as we studied last time, it is given from, it's a sigma of n equal to minus infinity to plus infinity xn e raised to jn omega naught t. Now xn we already know is 1 by t integral minus t by 2 to plus t by 2 x hat t e raised to minus jn omega naught t dt. So what we do is we substitute for xn from here. So what we get is x hat t, this sigma remains. For xn you substitute this entire integral, and of course this remains as it is. Now what you do, you apply the limit. So limit t approaching infinity, so x hat t becomes xt. This is limit t approaching infinity, and this entire equation that we had written earlier. So now as t approaches infinity, what happens? Omega naught becomes infinitesimally small. So 1 by t can be written as, instead of omega naught, we write as d omega because it becomes quite small now. So 1 by t can be written as d omega divided by 2 pi. So this 1 by t can be written as d omega divided by 2 pi. And as t approaches infinity, this integral becomes minus infinity to plus infinity. X hat t becomes xt, and this discrete n omega naught function becomes a continuous function. So when we write it like this, xt is limit of t approaching infinity x hat t, limit of t approaching. So now for 1 by t we have substituted d omega by 2 pi, and this is minus t by 2 to plus t by 2, etc. Now we put the limits, so this becomes minus infinity to plus infinity, and as t approaches infinity, this integral essentially becomes a, this summation sign essentially becomes an integral. So this is replaced by an integral as t approaches infinity. This is 1 by 2 pi. Now this is minus infinity to plus infinity e raised to minus jn minus j omega t and dt, and x hat t becomes xt. So you can write xt therefore as 1 by 2 pi is a constant, so I can take it outside the integral. Now if you look at this whole integral, it is essentially the Fourier transform of xt. So we substitute for this, that is your x omega into e raised to j omega t d omega. So what we wanted to do was to obtain the expression for xt in terms of x omega, and that is what we have done. So what are the results now? To summarize, x omega, which is the Fourier transform of xt, is given like this, and xt, which is the Fourier inverse of x omega, is given by this equation. So this is the Fourier transform of xt, and this is the Fourier inverse of x omega. So in short, you write it like this: x omega is Fourier transform of xt, and xt is Fourier inverse of x omega. Or further, in short, you use this double-sided arrow, and this means that x omega, note that this is not a equal sign. What it means is that x omega is a Fourier transform of xt, and xt is the Fourier inverse of x omega. Now you can write this equation in terms of f rather than in terms of omega, simply by substituting for omega. So this is 2 pi ft. So the left hand side can be expressed as a function of f rather than omega. And the inverse equation you can write, because omega is 2 pi f, so that 2 pi cancels. So you get this equation. Now if you look at the units of xt, remember that was obtained by multiplying xn by t, and t has the dimensions of reciprocal of frequency. Therefore units of xn are volts seconds, assuming that xt is a voltage signal. Otherwise it could be something else, but it essentially gets multiplied by time, or you can say volts per hertz. So I have written here volts, assuming that xt is a voltage signal, but if it is something else, then this would be replaced by that something else. All right. So if you express this in terms of f, then you find equations look a little more symmetrical. If you write this equation in terms of omega, then you get a factor of 1 by 2 pi. Of course, whether you use this or you use omega depends on which is the easier integral to evaluate. So in this session, we have studied what is Fourier transform. We have said it is used to calculate the frequency spectrum of a non-periodic signal, and we have obtained the expression for the Fourier transform. So if xt is given, you can find the Fourier transform, or if the Fourier transform is given, you can find the Fourier inverse, that is xt. And that's all in this session.